In 6.4, we'll be discussing arc length. So what do we mean by the length of a curve? We might think of fitting a piece of string to the curve which you see in figure 1, and then measuring the string against a ruler. But that might be difficult to do with much accuracy if we have a complicated curve. We need a precise definition for the length of an arc of a curve, so in the same spirit as the definitions we developed for the concepts of area and volume. Now, if the curve is a polygon, we can easily find its length. We just add the lengths of the line segments that form the polygon. Now we can use a distance formula to find the distance between the endpoints of each segment. We are going to define the length of a general curve by first approximating it by a polygon and then taking a limit as the number of segments of the polygon is increased. Now this process is familiar for the case of a circle, where the circumference is the limit of lengths of an inscribed polygons. And you can see here what happens here is you have now the square turns into these polygons to get it really close to that circle. Now suppose that a curve C is described by the parametric equations. We have x, which is equal to f of t, and y is equal to g of t, where t is in between a and b inclusive. Let's assume that C is smooth in the sense that the derivatives f prime of t and g prime of t are continuous and not simultaneously zero for t being in between a and b. Now this ensures that C has no sudden change in direction. Then we divide the parameter in the interval from a to b, inclusive, into n subintervals of equal width delta t. If we have the following t subscript 0, t subscript 1, t subscript 2, all the way to t subscript n are the endpoints of these subintervals, then x subscript I equals f of t subscript I, and y subscript I is equal to g of t subscript I are the coordinates of the following points: p subscript I, x subscript I, y subscript I, that lie on C and the polygon with vertices p subscript 0, p subscript 1, all the way to p subscript n, which approximates C. Now we can see that in figure 3 here. So here is your first point, there's your second point, your third, and so on. So you can see here what's happening is you're creating these segments. Now the length L of the curve C is approximately the length of this polygon, and the approximation gets better as we let n increase. Now if we look at figure 4, where the arc of the curve between p subscript I minus 1 and p subscript I has been magnified, and approximations with successively smaller values of delta t are shown. So here is the representation of the first segment, and then here we create sort of like what the polygon looked like, and then we get closer to the curve and then closer and closer to the curve. And then what we're doing is we're defining the length of C to be the limit of the lengths of these inscribed polygons. So you would have L, which is equal to the limit as n approaches infinity, where I is equal to 1 to n, of the distance from p subscript I minus 1 times p subscript I. Now again, distance is the absolute values because the distance must be positive. Now notice that the procedure for defining arc length is very similar to the procedure we used for defining area and volume. We divided the curve into a large number of small parts, and we then found the approximate lengths of the small parts and added them. And then finally, we took the limit as n approaches infinity. Now for computational purposes, we need a more convenient expression for L. Now, if we let delta x subscript I equal to x subscript I minus x subscript I minus 1 and delta y subscript I, which is equal to y subscript I minus y subscript I minus 1, then the length of the ith line segment of the polygon is the following. It would be the square root of delta x subscript I squared plus delta y subscript I squared. And that is the definition of the length, or the distance. Now, from the definition of a derivative, we know that f prime of t subscript I is approximately delta x subscript I divided by delta t, if delta t is small. Now, we could have used any sample point of t subscript I in place of t subscript I. So therefore, we can say that delta x subscript I is approximately f prime of t subscript I times delta t, and delta y subscript I is approximately g prime of t subscript I times delta t. And then what we do is we're then going to substitute this information into the distance formula. So we're going to replace those with the following to get that approximation. And then what we do here is then we're factoring out delta t. And then we get the limit with an approximation of I is equal to 1 to n of the square root of f prime of t subscript I squared plus g prime of t subscript I squared times delta t. And this becomes a Riemann sum for the function. And so our argument suggests that the length is equal to the integral from a to b of the following formula dt. And in fact, our reasoning can be made precise. This formula is correct provided that we rule out situations where a portion of the curve is traced out more than once.